We're starting section 14.3 today on line integrals over vector fields. And I have a graphic here to kind of remind you of the line integrals that we've already done in section 14.1. In section 14.1, we had this curve down in the XY plane, and we were looking at this sort of area of this curtain that was above the curve and trapped below a given surface. We're still going to have that curve to talk about in these line integrals over vector fields. And we're still going to parameterize those curves with a vector valued function r of t. So that's what this r is referring to. This is going to be the parameterization of that curve c. And now we have this vector field f. All right. And these line integrals over vector fields are going to have lots of applications. The one that's probably easiest to think about has to do with work. You might have learned in a high school physics class that work is equal to force times distance. And that's the underpinnings of this line integral over a vector field. And it's really the easiest way to understand what these line integrals might be able to do for us. So here we are on our Moodle page in the resources for the week. And I have a link for line integrals over vector fields in R2. So I'm going to click on that link. So we have a vector field drawn in this applet in blue arrows, and I want you to think of that vector field as some kind of velocity field, like a wind vector field or something like that. And our curve C is, in this case, the line segment going from A to B. They've got the little arrows of orientation there that we're traveling from A to B along this curve. And we're going to think of that curve as being a train track. And so think of like a little toy train track with a little toy train on it. And the wind is going to be pushing on that train. So when we calculate a line integral over a vector field, it's going to tell us how much work the wind is doing in pushing the toy train along the track. So here I've kind of got that curve oriented so it looks like the wind is blowing in the same direction the track is going. So we would calculate this one and find some positive work going. If I rearranged this so that the wind was blowing against the track, so if I kind of came down into this region, and now the wind is sort of blowing up and the train is trying to go down, we would get a negative work. So the work the wind is doing is sort of against the flow of the curve. And this is what it's going to calculate. All right, here's how we're going to calculate our line integrals over vector fields. We're going to have this vector field and we'll have a curve. So we have to parameterize the curve. So this r of t that we're talking about is that parameterization of the curve c. And then we're going to take that parameterization and plug it into our vector field f. And then we're going to dot that. So this is not multiplication. These are going to be vectors. So we're going to dot that with the derivative of the parameterization function. All right, so let's just give this a try. We have our vector field, capital F there. It's got x's and y's in it, a two-dimensional vector field. And C is our curve y equals x to the fourth from the point 0, 0 to the point 1, 1. All right, so the first thing we need to do is to parameterize that curve. Now, when you have a Cartesian equation like this, y equals x to the fourth, coming up with the parameterization is really pretty easy. So my parameterization, I'm just going to redefine x as t. So my x component is going to be t. And then since y is x to the fourth, the y component will just be t to the fourth. And then because my curve is going from x equals 0 to x equals 1, those are going to be my limits on t. So we'll say from t equals 0 to 1. So that part's done. All right, so looking at my red box down there, we're going to calculate this line integral, f dot dr. And it tells us to calculate from a to b. We just figured out the a to b was 0 to 1. And then the formula tells us to take f of r of t. So you're going to take your r of t function and plug it in to your vector field function. So I'm going to take my x formula, let's circle this in green, t, and I'm going to plug that in wherever there is an x in my vector field. So I'm going to plug in x equals t, and then wherever there's a y in my vector field, I'm going to plug in a t to the fourth. So that's only going to be one place here, t to the fourth. All right, so f of r of t is going to be the vector 3 times x squared, we plug in t for x, so 3 times t squared. Y, I'm plugging in t to the fourth, plus 2 times x, that's going to be 2 times t, comma. All right, so still looking at my capital F, the y component is x cubed plus 1. Plugging in the green stuff, t cubed plus 1. All right, so that was this part of the formula right there, that f of r of t. So plugging in the parameterization into the vector field, and then there is that dot product. So I said this was a dot product with r prime of t. So we're going to plug in the derivative of our parameterization. So our parameterization is t, derivative that would be 1. Derivative of t to the fourth would be 4t cubed dt. First of all, let's clean up that first vector. It's got a little bit of simplification to do. So this says integral 0 to 1, 3t squared times t to the 4th, that's 3t to the 6th plus 2t, comma, t cubed plus 1, and we're dotting that with 1, comma, 4t cubed. Okay, so been a while since we've done a dot product. Let's remember how to do that. We're going to multiply x components, and we're going to add to that multiplying y components. All right, so I'm going to have the integral from 0 to 1. Let's see, so I need 3t to the 6th plus 2t times 1, just the red underlines parts. So that's 3t to the 6th plus 2t, multiplying by 1 is easy. And then as a dot product, so I'm going to add. So I got my y components, the purple underline, t cubed plus 1 times 4t cubed. So I'm really going to be distributing that 4t cubed over those two terms. So that's going to give me 4t, add my exponents to the 6th, plus 4t cubed dt. And then I can combine those t to the 6th terms. This is just the integral from 0 to 1, 7t to the 6th plus 4t cubed plus 2t dt. I need a little more room, so let's clean off this slide. All right, so let's find this antiderivative. I'm going to integrate 7t to the 6th, so that's 7 times t to the 7th over 7, 4 times t to the 4th over 4, and then 2t squared over 2. Those are some magical coefficients. So then everything kind of drops out. My 2's cancel, 4's, 7's, and all of that is going to be evaluated 0 to 1. All right, so I'm going to plug in 1. Got 1 to the 7th plus 1 to the 4th plus 1 squared. And then I'm going to plug in 0 for t. It's a bunch of 0. And I've got 1 plus 1 plus 1 is 3. And that's going to be our answer. So here's the example that we just calculated. I've got the vector field drawn in blue there, and the curve is graphed in kind of a rainbow color. And we can see as we go from 0 to 1, the wind is kind of blowing in the same direction as the orientation of the curve. So it makes sense that we got a +3, positive work, because the wind was blowing in the same direction as the orientation of the curve. Let's try one more of these. This one has a 3-dimensional vector field and a 3-dimensional curve that is nicely already parameterized for us. So we're going to calculate the line integral f dot dr. And again, we're looking down in the box. We're going to integrate that from a to b. Thankfully, they've already told us that this curve goes from t equals 0 to 2 pi. Next, we're going to plug in our parameterization into the vector field. All right, so my parameterization has x component of cosine t. So I'm going to plug that in for x in the vector field. My y component is sine t. So I'm going to plug that in the x component up here, sine t. And the z component of the vector field is just 1. There's nothing to plug in there. All right, so the f of r of t part of this is going to be negative sine t, comma, cosine t, comma 1. And then we're going to dot that with r prime of t. So I'm going to take the derivative of that vector value function right above where I'm writing. Derivative of cosine is negative sine. Derivative of sine is cosine. And then the z component of that parameterization is t over 2 pi. You could think of that as being 1 over 2 pi times t. That 1 over 2 pi is just a coefficient, like a 3 or something like that. So the derivative of that z component is just going to be 1 over 2 pi. So now we're ready to calculate that dot product and move on with the line integral. All right, so we've got the integral from 0 to 2 pi. And we're going to multiply component-wise. I'm going to multiply x components. Negative sine times negative sine gives me sine squared. Dot product, so I'm adding. I'm going to multiply y components. And I get cosine times cosine. And then multiply z components. 1 times 1 over 2 pi. Adding because it's a dot product, and I get 1 over 2 pi. With my dt at the end. All right, so this ended up being a lovely integral. I got sine squared plus cosine squared. We know that's just equal to 1. So this whole integral is just 0 to 2 pi of 1 plus 1 over 2 pi. All right, and that's a really nice integral. That 1 plus 1 over 2 pi, that's just a constant. It's like a big 5 sitting in the middle of the integral. All we got to do is put a t on it to find the antiderivative. So I'm going to have 1 plus 1 over 2 pi, all of that constant times a t, and then we'll evaluate that from 0 to 2 pi. All right, so we've got 1 plus 1 over 2 pi times 2 pi minus 1 plus 1 over 2 pi times 0. All right, just to make this look prettier, I'm going to distribute this 2 pi, and I get 2 pi, and then 1 over 2 pi times 2 pi is just 1. And then everything else over here is just a big 0 that goes away, and our answer is 2 pi plus 1. So again, I went ahead and graphed this vector field for us and the curve. And again, our orientation is going to be from 0 to 2 pi. So you want to think about this as a roller coaster, maybe going up, and our wind vector field pushing up again in the same direction as the orientation of the curve. And so we got a positive value of work, 2 pi plus 1, done along this curve by the vector field.